Okay, so we're all roughly back from lunch, so let's crack on because, as I say, time is an issue with these things. We've got things pretty densely packed in this afternoon. So this afternoon we are going to be sort of dealing with things more at perhaps the quantum end of the scale, and we are going to kick things off with Sabine Hossenfelder from Frankfurt, who is going to tell us some interesting things about naturalness with a quite provocative title.
Yes, so thank you for the introduction. When I looked at the abstracts, I noticed that I have the wrong title. So this is the title that I sent to another workshop where I'm going. But it's the same talk, so don't worry. I'm very grateful for the opportunity to speak here about the topic of naturalness and fine-tuning because it's been on my mind for a long time. Not because I think it's interesting, but because I think it's not interesting, and I find it interesting that so many people find it interesting. So this might be the first time that you hear a talk where the speaker tries to convince you that the topic is not interesting. Okay, so I promised that I would say a few words about the history of naturalness, so I'm not much of a historian, but I'll do my best. So what you see there is an artist's impression of the geocentric model with the Earth in the center and the Moon and the Sun going around. And then at the far distance, there is the celestial sphere with the stars that are pinned to it. And as you all know, that ran into conflict with observations at some point because it's difficult to explain the observed motions of the planets with that. Some people started to think that maybe it would be better if the sun was in the center. So that's a heliocentric model. But there was a problem with that that caused them to reject this idea, which is that if the sun is in the center and the Earth moves around it, then the stars should move, because over the course of the year, our distance to this sphere would change. So the orientation of the stars towards each other should change, and they didn't observe any change during the course of the year. So they concluded that if there is any change, it has to be really, really tiny, which meant that this sphere had to be very, very far away. So that was one thing that they noticed. The other thing was that they also measured the size of the stars as they observed them in their telescopes. And now at this time, which was sometime in the 17th century or so, they had, well, not very good telescopes. So what they saw of these stars was basically a blurry point. There was mostly diffraction, but they didn't know very much about optics. So they thought that what they saw, this blurry spot, was the actual size of the stars. So if you add this both together, they were now thinking that, well, these stars have to be very, very far away, and they also have to be gigantically large, much larger than our own sun, and they thought that this is absurd. So that isn't how it should be. Now, this, I think, is best expressed in this quote from Tycho Brahe. It is necessary to preserve in these matters some decent proportion, lest things reach out to infinity and the just symmetry of creatures and visible things concerning size and distance be abandoned. It is necessary to preserve this symmetry because God, the author of the universe, loves appropriate order, not confusion and disorder. So then I've highlighted here the decent proportion and appropriate order, which I think is basically the idea of naturalness that we are still using today. So Brahe, for this reason, rejected the heliocentric model and cooked up his own model, which was a hybrid of the geocentric and the heliocentric model, in which the Earth was still in the center, the sun went around it, and the other planets went around the sun, or something like this. so a little bit confused. So today, of course, we know, well, one thing that we know how optics works. So we understand now that they were mistaken in thinking that the stars have to be huge. We also know that the stars do indeed move over the course of the year. So this parallax was measured only 2 centuries after they tried to measure it. So it's tiny and it's hard to measure. We also know that there is nothing wrong with the stars being far away, because we should not expect the stars to be at a similar distance as the other planets. These distances come about in a very complicated process during structure formation in the universe, and this distance to the stars that we observe is perfectly natural, so there's nothing inappropriate about this order. But this idea of decent proportion and appropriate order carried on, so I'm skipping a few centuries here, to Dirac, who formulated what is called the large number hypothesis. So there were a few other people in between that I'm skipping over, like Eddington and Weil and so on, who played around with numerical coincidences. But here's the observation that Dirac made. On the left side, you have the age of the universe divided by the time it takes light to cross an atom, so basically the Bohr radius. And on the other side, you have the ratio, and we saw this already earlier this morning, the ratio of the electromagnetic force between an electron and a proton, and the gravitational force between electron and proton. So these are not actually the forces, but the forces go both with 1 over r squared, and the 1 over r squared cancels out. So this ratio on the right side is something like 5 times 10 to the 39, and the ratio on the left side is something like 2.5 times 10 to the 39. So they're not exactly equal, but they're pretty close. And Dirac thought that this should not be a coincidence. So he thought there must be something to this. And actually, he didn't stop there with these 2 large numbers, but he went further and said that actually all large numbers that we observe should be related in some way. Any 2 of the very large dimensionless numbers occurring in nature are connected by a simple mathematical relation in which the coefficients are of the order of magnitude unity. So here's where this appears with the magnitude unity, which is still the way that we formulate today this idea of naturalness. Okay, there is an obvious problem with that relation that he's written down there, because the age of the universe depends on the age of the universe. So it's not a constant, it changes with time. So if you want this relation to hold for all times, then you need to make one of these other constants that are also time dependent, and the one that Dirac picked is Newton's constant. And that causes all kinds of tensions with general relativity, and it has a host of observational consequences which are in conflict with observation. So this hypothesis was ruled out before I was born, sometime in the early 70s. Though maybe I shouldn't say it was ruled out, because you know how it is. There are always like 1, 2 people who still work on this. Okay, but yeah, so much about the large number hypothesis. So I forgot to put something in here which I wanted to read to you. It's a quote from the historian Helge Krag about Dirac. So he did this sometime in the 1940s. After 1935, Dirac largely failed to produce physics of lasting value. It is not irrelevant to point out that the principle of mathematical beauty governed his thinking only during the later period. So you probably all know there are a lot of quotes from Paul Dirac where he emphasizes the relevance of mathematical beauty, like the researcher in his work should strive mainly for mathematical beauty and that kind of thing. So, and I think we see this this belief in beauty reflected in this playing around with the numbers here. Okay, so there isn't, strictly speaking, any precise definition for naturalness, but I think that in the theoretical physics community, we all more or less mean the same thing when we speak of naturalness in a general way. It's that dimensionless numbers shouldn't be much larger or smaller than 1. So it doesn't matter if they are larger or smaller than 1, because you could always take the inverse. A number that is not natural is fine-tuned. So fine-tuning here means just the opposite of naturalness. And I have to warn you that this is a little bit different use of the word fine-tuning than what we heard in the morning. So there, fine-tuned is always a statement about a number being large or small. It's not necessarily fine-tuned for the existence of light in the universe or something. But the gist of this is basically the same. They require an explanation. A fine-tuned number is considered unlikely, and that's why we want to try to construct some argument for why that number would have a particular value. So this is naturalness in general. Then in high-energy particle physics, there is a more specific version of naturalness, which is technical naturalness, that applies only in the context of quantum field theory. If you have a dimensionless number in a quantum field theory, which is much smaller than 1, it must be protected by a symmetry, or more generally, the smallness must be explained by some underlying physics. So this goes back to Hooft, who emphasized the relevance of symmetries. Another way to put this is that naturalness requires that the numbers are not highly sensitive to the theory at high energies in the ultraviolet, which is presumed to be more fundamental because we believe in reductionism, basically. And there are various quantitative measures for the naturalness of a quantum field theory, which are being used in the literature. So you see, this is why I had this subtitle of my talk, How Religion Turned into Mathematics. So we've moved from this reference to God and the appropriate proportions to a mathematical definition of what it means for something to be natural. And so I have an image to show you what this means with the sensitivity to the ultraviolet. So the quantum field theories that we use, they depend on the scale at which we probe the theory. So they are all energy dependent via the parameters that occur in the theory. So this is called the renormalization group flow. And this means that one can picture all quantum field theories that there are in a theory space. So every point in theory space is a quantum field theory, and as you change the energy scale, so that's then the theories flow through the space. And I've shown you here schematically how theories could flow from high energies to low energies. So you might not think of it this way, but in theoretical high energy physics, the standard model is the low energy theory. So the standard model would be somewhere here, and in the ultraviolet at high energies where you would have the grand unified theories or something like this. So the theory at low energy is not fine-tuned. If it basically doesn't really matter what you do in the ultraviolet, you always flow down to the standard model. On the other hand, if you have a situation which is like this shown here, so the standard model would be somewhere there, then you would have to very precisely pick your initial value to actually get to the right point. So this would be a fine-tuned theory. That's a not fine-tuned theory. And naturalness works. There are a couple of examples that are commonly mentioned for naturalness that many of you probably have heard of before, so I only want to mention them very briefly. So there's the question, why is the electron mass so small? If you calculate the self-energy of the electron, it makes a contribution to the electron mass, which is technically infinitely large. Of course, that shouldn't be the case. So you can assume that at some small distance scale, or respectively at some energy scale, you cut off this contribution, and then you get an additional term that depends on the cutoff that you have assumed. And this leads you to predict that if this additional term that you get from the self-energy contribution should not be much larger than the mass that we observe, then the cutoff of this theory has to be no later than 70 MeV or something like this. And indeed, if you look at the observation, that is the case already earlier, because at 500 keV you find the positron, which basically tells you that you have to take into account quantum field theoretical effects. So this is not how it historically came about, but you could interpret it this way. There's also the smallness of the difference between the mass of the neutral and charged pions, which is suspiciously small. And you can, again, calculate the contribution to this mass difference, and in an effective theory, you assume that this theory has a cutoff, and you get a typical size for this difference that you would expect depending on the cutoff. And then you can say, well, we observe that it is so and so small, at which point would this new theory have to become relevant? And you find, well, it would be somewhere at 850 MeV. So that's the latest at which we have to observe that this theory must be superseded by a more fundamental theory, and indeed this is the case. So at 770 MeV you find the Rho meson. So this also was not a prediction, it was an observation made after the Rho meson was observed. There is, to my knowledge, only one prediction that has ever been made using arguments from naturalness, which is the prediction of the charm quark. So in the standard model, flavor-changing neutral currents are suspiciously absent. There isn't any good reason, if you have three quarks, there isn't any good reason why these contributions should be absent. And you can use this again to make an estimate for when would new physics have to occur, depending on some cutoff of the theory. And you find that it has to occur no later than 2 GeV. And indeed, new physics comes in form of the charm quark, which has a mass of 1.3 GeV. So if you have 4 quarks, so this was the 4th quark, then these terms are naturally absent. Okay, so the masses of the standard model are all natural, except for the mass of the Higgs, and I will say a little bit more about the mass of the Higgs. In fact, the standard model is completely natural. Not that it was constructed by trying to make it natural, but it's an observation that one can make. It is, in fact, technically natural. But sometimes naturalness does not work. We have already heard the best known example, which is the cosmological constant, which is 30 orders of magnitude smaller than what the Planck scale cutoff suggests. I'm referring to the energy scale, not to the energy density, because I find this a little bit misleading, that you get this. It's normally quoted as 120 orders of magnitude because one speaks about the energy density, but in no other context do we normally speak about the energy density. So it's 30 orders of magnitude. Then where's the axion? interaction violates CP symmetry. The electromagnetic interaction cannot violate it, but the strong interaction can violate it but doesn't. So there's a term that one can write down that for some reason has a prefactor which is either 0 or very, very small. If that was not the case, we would see an electric dipole moment of the neutron, which we haven't seen. So this is known as the strong CP problem. So there's a parameter called theta, which has to be very small. Nobody knows why. So one can solve this problem the way that people in the field like to solve problems. You make this parameter into a field, and then the field gets a potential, and the value of the parameter approaches the minimum of the potential, and that way you can solve this problem. That was proposed by Apache and Quinn, and only a few years later it was pointed out by Wilczek and Weinberg independently that, well, if you make this parameter into a field, then there should be a particle associated to it, and that particle is called the axion. And that axion was looked for and it wasn't found. And it was very quickly ruled out within a couple of years. And then the axion models were amended to something that's called the invisible axion, which is basically much weaker coupled. And well, people have looked for it since the 80s or something, and I haven't found it. Then there's the Higgs mass. The Higgs mass is 15 orders of magnitude smaller than what the Planck scale cutoff suggests. So the Higgs mass gets contributions from quantum fluctuations that should be of the order of the cutoff of the theory. And if you want to get rid of them, you would need to have a bare mass for the Higgs, which is almost identical to the except for the sign, to the corrections from the quantum fluctuations. And that would require that these two constants are very, very close to each other, but not exactly identical. So that would require fine-tuning. And then there's the WIMP miracle, which isn't really technical naturalness, but I wanted to mention it anyway. So the WIMP miracle, so WIMP is a weakly interacting mass of particles. It's the most popular candidate for dark matter. So if you assume that this is, for example, some supersymmetric particle or something like this, which has a typical mass of some 100 GeV, and you calculate the abundance of these particles, how they are produced in the early universe, it comes out just right for it to make up dark matter. And yeah, well, they've looked for WIMPs and I haven't found them. So much about that. Now a little bit more about the Higgs mass. So we knew that the LHC would have to find some new physics, not because of a naturalness argument, but because the standard model without the Higgs is not unitary at LHC scale. So we knew that there something had to happen at the LHC. It wouldn't have been necessary to necessarily have been the Higgs, but something. So that was not a naturalness argument. But naturalness arguments have certainly been used to motivate why the LHC should also find something else. The most prominent theory being supersymmetry. But you know, there were other candidates that came and went, like large extra dimensions or something like that. You know, black holes at the LHC, this whole story. And these were all based on naturalness arguments. You find that all over the literature. Now, nobody wants to have said it, but okay. So that was the story. The way that this works is that the mass of the Higgs would not be natural unless there is some new physics which helps to cancel these contributions. And supersymmetry is a good example which does exactly this. So if you have a supersymmetry, then these troublesome contributions from the quantum fluctuations to the Higgs mass cancel. If a supersymmetry would actually hold, then they would cancel exactly. But we know it has to be broken because we haven't seen it. So then you are left with a contribution which is about the size of the symmetry breaking scale. scale or the mass of the first particle that enters these loops. That was an argument why the LHC should find supersymmetry, because that would be required to make the Higgs mass natural. Okay, but so far the LHC hasn't found it. And actually right now already the parameters are pushed so much to high energies that we already know that the standard model just isn't natural. So it could still be that supersymmetry is there. The data hasn't been so well analyzed, but we already know it's not natural. Okay, so what's the problem with naturalness? So let me maybe start with reminding you of this image I showed of the flow in theory space, where I said, well, if these theories start very far away up here and they all flow together, then this is a natural theory, and if it's the other way around, that they diverge from each other, then this is not a natural theory. Well, that requires that you have some probability distribution in this theory space. And where does this probability distribution come from? It cannot come from the theory itself, because it's a distribution over theories. So the only way that you can make this argument is if you assume a probability distribution on this space. This is necessary. And indeed, if you try to compute any of these naturalness measures, you implicitly make an assumption that you have a probability distribution, which is typically something that is a uniform distribution over an interval from 0 to 1, something like this. Where does this probability distribution come from? Yeah, so it will work out somehow. Well, you have to choose it. There's a problem with this, because if you have to make a choice, you could as well just have chosen a constant. Okay, the whole point of having these arguments from naturalness was that we try to get rid of human choice. Okay, so a more general argument for why I think naturalness is a useless argument is that we already know that all theories that we can write down are infinitely fine-tuned and not natural anyway. Because whatever theory you want to write down needs to have some axioms. There are infinitely many mathematically consistent sets of axioms. So you need to choose some. Where does this choice come from? The only argument that you can draw upon is that it describes observation. And then you can complain, well, but this was fine-tuned. Okay, so I think that there is no rationale for arguments from naturalness. So there are more general argument for technical naturalness. If you have a theory of everything, and there is this one theory that you have written down, what distribution are we even talking about? The whole point of having the theory of everything is that there's no distribution for this theory. And why do we fix the parameters and the Planck scale to begin with? And why don't we fix them down in the infrared? So I think that naturalness is not a mathematical criterion, it's an aesthetic criterion. And in addition to this, it's a hypothesis with a very questionable track record. It has made exactly one prediction, and it has a couple of failures. Okay, so I have 5 minutes or something, which is not much, so I'll only go through this very briefly. Inflation was meant to solve 3 fine-tuning problems, but actually it doesn't solve any of them. We already know this, so from the data that we have now, because inflation itself needs to be fine-tuned, the potential has to be fine-tuned. Yeah, I think I'll leave it at this because I'd rather say something else. So the consequence is, if you sum it all up, what do we know about naturalness? Well, we know that sometimes it works, so sometimes it doesn't work. Okay, so I don't want to say that we should throw out naturalness, because because it seems to be something to it in the context of quantum field theory, in particular the standard model. But I think the problem with naturalness is that we can't properly use it because we don't understand coincidence. We don't really know what we're even talking about with the distribution of these theories, with the distribution of the parameters. What do we mean by making a choice for the axioms of a theory or something like this? Well, believing that fine-tuning is a problem didn't really get us anywhere. There have been lots of consequences for experiments. There have been, since 30 years, people have looked for WIMPs. They haven't found any. They've looked for axions. They haven't found any. Super partners should have been found at lab already in the 1990s. That was before I even started studying physics. They still haven't found them. There are a lot of fields that have been invented to explain the cosmological constant. I recently read a survey on inflationary models. There are like 200 different potentials that people have thought of. And these are only the single field potentials. And yeah, so I'm not sure what really do we learn from this. I don't want to scare you, but there are infinitely many potentials that one can think of. So I think what we do learn from this is that theoretical physicists are really good at writing papers. So personally, for what I'm concerned is, I think a constant parameter is pretty much the simplest axiom that I can think of. Getting rid of this parameter and replacing it with various fields and potentials of these fields, and then these bring in their own problems and so on, doesn't help anything, doesn't make the theory better. Okay, consequences for theory. Well, we lose time because we're hitting on problems that are not actually problems. And it has been said many times before, there has not been a lot of progress since the development of the standard model. And now we have a lot of multiverses. So how does this come about? Well, the problem is that if you have a theory and you try to make it a simpler theory, you want to get rid of your axioms, at some point the theory becomes ambiguous. And what you get then is you get a multiverse. You can do this with any theory that you have. If you remove sufficiently many axioms from your theory, then you get a multiverse. And that's what we see here. So let me point this out once again. If you want to construct a theory that describes our observations, you always need to pick assumptions that come from observations. You cannot do it based on mathematical consistency alone. It's not possible. The only way to avoid this is that you go the way of Tegmark's mathematical universe, in which you just postulate, well, everything that's mathematically consistent is also real in some sense. So I don't want to get into the philosophy of what this might mean. But that's basically his idea. Well, what do you have then? Well, you have replaced the question for why do we have this theory with these axioms with why are we in this particular place in the mathematical multiverse? And I'm not sure what we learn from this. The same question, dressed differently. Okay, so I'm almost done, and next slide is the last one. So I think naturalness is one example of a more general reliance on beauty that has taken hold in theoretical physics since the development of the standard model, that I think has convinced many theoretical physicists that the power of their mind is sufficient to find out what nature wants. Besides naturalness, which has the problem that it's ill-defined, as I pointed out, there's also simplicity, which is now typically pursued in form of a dropping of axioms or unifying principles, like combining several symmetry groups to one larger symmetry group. The problem with simplicity is that simplicity cannot be used as an absolute criterion. It can be used to distinguish between different theories. You can say, well, this one is simpler than this one. But simplicity in and by itself doesn't help you very much because we already know that the universe we live in is not the simplest that you can think of. You know, the universe would be simpler if there was no matter in it, but we just don't live in that universe. What's also often drawn upon is elegance, so that's basically surprising consequences that come from sparsity. And I should have said that these are not definitions that I've looked up somewhere, and these are not definitions that I want to propose. This is basically what I have extracted from what I see, how the words are being used. The problem with elegance is that what's surprising, what is not surprising, depends on what you expected in the first place. And that also depends on your education and your exposure to the material. And beauty is a combination of all of the above. Okay, so that's my last slide. So I hope that I have convinced you that naturalness is not a mathematical criterion. It's depending on your attitude, it's either an aesthetic criterion or a philosophical one. That doesn't mean it's wrong. You can certainly use it as an assumption to construct your theories, but if it doesn't work as a hypothesis, you have to draw consequences from this and revise it. More generally, I think we need to rethink what is and isn't a problem in the foundations of physics. Personally, I don't think that if you have some unexplained parameter that just sits there, that's not a problem worth of investigation. I would want to put forward that if intuition fails, like this feeling that you have, if there's a number that's 10 to the minus 30 or something that screams for an explanation, if that intuition fails, then what we need is more mathematical rigor and not less. Thank you for your attention.
Okay, so time for a few questions. Yeah.
Well, thanks for a very thought-provoking talk. Just a point on, well, one could say a point on rigor regarding what LHC has actually shown and not shown. So there are models, supersymmetric models, where you have gluino masses of 500 GeV, superpartners in that range, not multi-TeV. They are basically what one would say natural supersymmetric models. And these, I would say, and these are not excluded by experiment. Yeah. The difference between what you're referring to, sort of multi-TeV bounds, is that the multi-TeV bounds refers to models in which you have all superpartners decaying into one single particle in the standard model. So these are simplified models. They were designed to be sort of discovery vehicles, but for constraints they're not that good, and they're now used to set these very high constraints. But I don't think we can currently interpret the results from LHC that all supersymmetric models that are natural have been ruled out, because I mean there are examples to the contrary. So could you comment on that, please?
Yeah, sorry, I was thinking I would need the microphone then. Sure, you know, depends on what exactly you mean with naturalness.
Okay, so no large group corrections?
I'm pretty sure you can always make up some model by which this is possible.
Perhaps just postpone this to the later discussion. Further questions? Okay, seems we've come to a natural conclusion. Let's thank our speaker again.